Good morning. Hey, Caleb, are you on? Hmm. Okay. And is Sarah on, or are you going to start the meeting? Oh, do I have to unmute you? Okay, hang on. Let me find you. There you are. Allow mic. Okay. Caleb, try it now.
Yeah, perfect. Can you
Okay.
hear me now?
All right. I can. Yep.
Perfect. I was waving for the first minute. I was hoping that you see me, but then I realized my camera was off. So, anyways, thank you everyone for joining. I think we can wait for 1 or 2 minutes just to have more people joining. Uh, but by this time, I can give a brief intro about Tim here. So, Tim is the regional vice president for GPS in Charlotte, North Carolina. He's a licensed professional engineer with more than 25 years of experience and has in-depth knowledge in designing and building commercial mechanical and control systems, specifically focused on healthcare and clean room applications. He spent many years working with a national field service business on the understanding of service reliability and preventative maintenance solutions. Today, in addition to supporting the Northeast, Latin America, and Caribbean territories, Tim handles corporate relationships with large commercial customers on developing and supporting strategic solutions uh, geared to support their sustainable and energy initiatives. Please welcome Tim Boyd.
Thank you, Caleb. Appreciate it. Good morning, everybody. So I am going to share my screen. I'm going to ask Caleb if you can just confirm that you see it, and then we'll get right into the presentation. And then at the end of the presentation, we'll do some question and answer, and I'm probably going to need some help on how to unmute everybody at that point, but I assume right now everybody's muted. So let me share my screen, and then we'll get into it.
Yep.
Okay, I'm going to go full screen. I was having a little bit of problems last week with this, but hopefully my IT team solved it. Can you now see the full screen?
Yeah, looks good, Tim.
Okay, great. I'm going to turn my camera off just for bandwidth issues, and then I'll go. Actually, well, maybe I guess I can leave it on, but I'll be sitting on this way. Um, okay, so the point of what we want to talk about today is the new standard known as 241. The electronic air cleaner lands underneath 241. And so what I'm going to do is I'm going to actually describe what 241 is, how it came to be, and then I'll actually walk into how air cleaners actually arrive underneath 241. And we'll get into the details of the actual standard. So you're going to learn today a lot about not just what 241 is and how to design it, but also how to evaluate the products that you plan to apply there. For those who have questions, you're welcome to add them to the chat, and I'll try to stop and answer them on the as we go through. Otherwise, I'll have to figure out how to unmute. You will get this slide deck, so anybody who wants it, you're welcome to get this at the end as well. But just to maybe give a little background onto what is 241 and how it came to be. So at the end of the pandemic, the ASHRAE team that was formed for the pandemic, so they were known as the Epidemic Task Force, they actually were disbanding, but they were asked by the COVID response team from the White House to put together a document that effectively, addresses what do we do in case we have to do this again. Basically, what do we do in case of the next pandemic or an endemic, or how do we actually provide better control within a space? And really, what they were asking is what did we learn, and can we actually improve the airspaces for viral control based on what we learned? And that's really what this document is intended to be. So the agenda is going to look like this. I'm going to walk through some key terms. I'm going to walk through the scope of 241. I'll then get into some new terms and how we actually use those for calculation. I'll go through a comparative between 241 and the existing ventilation requirements that are out there today, so you can see that. I'll also then kind of walk through the requirements, as I mentioned, for what air cleaners are. We'll go through a test report. We'll talk about how filters are added into this and what the requirements for filtration is. And then as like any good ASHRAE standard, they created a calculator. And so I'll show you the calculator as well. And then we'll conclude with a little bit of context and some Q&A. You're also going to notice this. So this is our opportunity to kind of pause. And this is where I would read the chats. And if I can get you guys off mute, allow you to come off mute here. But effectively, what I want to do during this conversation is give you a chance to kind of ask questions as to what you see in your world, what you're designing for, and potentially how what we're learning can be applied. And we're going to call this kind of the engineer's perspective. And so the first perspective and the first takeaway, or the first question we can ask, is we were going through the pandemic. There was a lot of things, if you recall, for those of you who were designing during that time, a lot was being thrown at us as to what the latest updates were. We're getting stuff from all sorts of sources, World Health Organization, the White House, healthcare systems, all these things were coming at us. And the question is, did we make good choices? And if you think about what was being designed at that time or what you were recommending to your clients, you can now go back and see, you can calculate what happened in that space based on what you recommended. You can also evaluate those products that you were recommending to put in. Do they actually meet the standard of today? And so let's kind of get into this idea of what is infection risk management and how it actually lands within the 241 parameter and how we can speak about it. So 241 introduced two new terms, and the first term, they both make sense, but the first term is really just a mode. So effectively, when you design a building today, you design it for normal mode, right? Normal operation. You would design it for night setback mode, right? What do you do in case people leave? So you can lower the air intake from the building, potentially save energy doing that way. You might find you're also going to design it by code for fire mode. I'll give you a good example. Typically, air stairwells, they'll have specifically larger stairwells or high building stairwells. They'll have pressurized fans so that if the building is normally pressurizing out into the stairwell during a fire event, you would actually have to pressurize that space to push air out to make that a safe egress pathway. And that's something that the fire marshal will come out once a year, typically, and test, right? So there are these types of modes that we have to make buildings safer. They're now adding what they call an infection risk management mode. And in this mode, the intent and the idea is you can roll in, turn on, add, incorporate some aspects to the building and to your mechanical systems that would improve the quality of the air such that you can lower the infection risk within that space. And the way in which you would calculate that is known as the equivalent clean airflow rate. You'll note you will call it ECA. You'll notice there's an I next to it. It's an important distinction here, but I stands for infection in the future, ASHRAE is actually using this concept of equivalent clean air for some concepts around what do we do about gas and particles as well under the IAQP within 621. That's not for today's PDH, but just recognize that's what the I stands for. It stands for infection. And there's this concept of you can add outdoor air, right? So you can always add more outdoor air at the expense of the unit, the expense of the operating cost, bigger units, more operating costs, and that would help dilute the space. But you can also exchange, instead of adding outdoor air to make a space safer, what if you can add cleaned air? And that cleaned air has to meet a certain parameter by which you can both clean the space without providing, while making it safer for people to breathe. And they call that calculation under the ECA. So they call it equivalent clean air. And so you'll notice you can use outdoor air as a calculation for ECA. You can use air that's being disaffected by air cleaners. You can also use filtered air that you're recirculating as a part of the calculation. And so this ECA actually is something that becomes pretty helpful to understand as we start to lay out these calculations. I'd like to also kind of point you to the introduction that's in front of 241. If you haven't had time or you haven't done so, I would ask that you spend just a few minutes and read the introduction. It's about a page and a half or so. But in it, they actually do make some interesting comments. So one of the comments is they in some ways do a mea culpa, where they note that the community has taken their eye off of indoor air quality at the expense of indoor air quality throughout the pandemic, as we learned. But they did it for various good reasons. So things like refrigerant control, decarbonization, energy aspects, all these other things that ASHRAE is focused on. And so what they've mentioned in this introduction is that they would like to double down and really now start to focus on the indoor air quality aspect of solutions within our space. And you can see here in this text that I've laid out that the requirements for filter and air cleaning tests incorporated in this standard go well beyond what is found in current standards. They are a major step in the direction of creating a uniform and effective technology agnostic criteria for performance and safety. Ultimately, this should enable more widespread and confidence in applying these technologies. What they're effectively saying is there's a lot of stuff that the OEMs were saying that, hey, we could do this, this, and this, and everybody was kind of using different standards and different tests and even creating their own tests. And what this now provides you as the engineer and you as the designer and the owner is the ability to say, look, here is the benchmark. If these tests can meet these benchmarks, or if this product can actually meet the tests that are laid out within the benchmark, then these are good and this should give you confidence. And so let's unpack that as we go through this. You'll notice here a lot of stuff on this particular page, but what I want to kind of highlight is, hang on, let me admit the mirror. Okay. What I want to highlight here is on the left, you'll see that this standard, the 241 standard, does not replace any of the existing standard. It's actually added as a complement. So meaning it's above these other standards. So if you're designing a commercial space, you would today design under 62.1. A residential would be 62.2, and a healthcare would be 170. You have to still meet those requirements. They're prerequisite before you enter 241. Notice that the test is that the test for the air cleaners have triplicate testing for effectiveness and duplicate testing for safety. There's a method by which you can scale this, so you can actually test. You can find out how much this is actually, what volume of air or what square footage can this product effectively provide for. And then there's a way for you to compare various different technologies. So you can have all these various technologies not within the same category, but they can get compared here. And then on the right, and we'll go through these, but I show you this just to give you an idea of how exhaustive the testing is. And so under the Appendix A, you can see there is a very large amount of tests, all pointing to various different ANSI standards, ISO standards, UL standards, and so on, that are now part of the requirement. And I would tell you, these are something that you might want to consider adding into your spec. So if you're designing for an electronic air cleaner, you would put in the spec that it must meet the safety requirements of 241 under Appendix A. It's a very simple add, and it actually now sets the benchmark for the products that you're designing for. Okay, so let's pause. Feel free to add a chat here. But the question in this that I want to go through here are, what are the aspects of ECA that, I want to make sure you guys take away? The first is that equivalent clean air doesn't replace any other existing standard. It's a supplement to all these standards. So standard 241 supplements the addition of everything else you're doing within these other standards, 621, 622, 70. Hopefully you understand this concept of ECA and IRMM. If not, we can go into it. We often get questions during this time about what products do apply. So what what products are you currently specifying for? Well, it could be soft ionization products, it could be hard ionization products, UVC, photocatalytic oxidation, hydrogen peroxide. All of these products will comply are appropriate for use so long as they meet the safety limits for generating ozone, the safety limits for formaldehyde, and the safety limits for particles. Again, I'll get into the safety piece of here, but this kind of gives you the ability to say, okay, which ones am I recommending today, and would I be comfortable recommending them in the future? Okay, so this is the heart. This slide here is the heart of your ECA calculation, and so I'll kind of spend a little bit of time here. On the left is a very simple equation, and it says, look, what is the volume of equivalent clean air that you need? It is going to be the ECA number that we're going to see there in the category on the right times the P sub Z number, basically the number of people that you're allowing in that space. And recognize it says P sub Z, comma, IRMM. What's important to note here is you don't necessarily need to have the same number of people in the space during an IRMM. So to give you a good example, we're going to walk through a school. We likely would keep the people at the same number. Why? Because we want to keep the school open. We want kids to continue to learn. We don't want to go back to this learning at home concept for those of you who had to deal with that. That would be a similar P sub Z to the regular amount of people that you would design under 621. I'll give you an alternate idea of this. Let's say you have a waiting area. Waiting area might hold a certain number of people. During the P sub Z, you might ask half of those people to wait in their car before they come in. They may have to wait up a text or a phone. If you recall, that's kind of how we were managing during the pandemic. We'd wait in our car and then we'd go in when called upon. So you can have a P sub Z there in that way. There's a question, so hang on, let me stop and find out.
It's just about there's a slide issue. One of the Dean was not able to see the slide, so I'm just checking with them. We're good.
Okay. All right, so on the right, you'll see a table. And notice the table is listed as CFM per person, so it's fairly easy to calculate. We're going to go through two calculations, so let me just kind of highlight what's important on this table. Notice, let's just take education. We're going to do a classroom calculation. So the classroom calculation requires, under this 241 standard, 40 CFM per person. So at first you might say, whoa, that's a lot of air per person, right? Because you're used to designing for outdoor air, and you probably design somewhere plus or minus around 10 CFM a person. Depending on your code and your locale, you might be at 7.5. But 10 CFM per person, 30 people, you might say, okay, that's 300 people or 300 CFM. Now, if you got to do 40, that's a lot of outdoor air. Now you can see why what they've done here is they've said, look, you can add other things to supplement that 10 that you're already doing. You don't need to do all 40 as outdoor air. You're welcome to, but that's a very expensive proposition. Also notice that if you were to scan your eyes up and down this list, that what ASHRAE's laid out here, these categories are laid out by risk profile. So for instance, if I were to ask you where the highest level of risk might be, you would probably think about it and go, probably where people are sick, so probably in a healthcare space. And sure enough, if you look at the healthcare, probably in a waiting room would be your highest level of risk. And so in fact, that is the case here. So if you look, the waiting room of a healthcare requires 90 CFM per person of equivalent clean air. It's a lot of air, right? But it's an indication that there's also a higher level of risk there. I travel a lot on a plane, so look at transportation. Transportation has 60 CFM per person. Is it on this chart? No, I'm doing it from memory, so you're not seeing it. But just recognize that as you go up and down this list, where you have higher people congregating or where you have a congregation of people, schools, office spaces, assembly halls, those spaces should be higher. The gate in front of your transportation, those would be higher. And then as you get into places where you're going to actually have known sick people, like healthcare, they'd even get higher still. Okay, so let's do a comparative now. So if I look at the existing standards, you'll notice that you have requirements for outdoor air, the minimum filtration as listed under this section 5, I think it is a MERV 8. If you exceed the EPA limits in 62.1, 62.2 and such, you have to go to a MERV 11, but you don't need a MERV 11. And they also spell out things like UVC. What's different, if you look at 241 now, is a MERV 8 gets no credit. You need to actually have a MERV 11A as of today. So what is an A, right? You know what a MERV 11 is. For those who don't know what an A is effectively a test whereby you're not just doing a single pass test in the way the manufacturer sends it to you, but you're actually discharging that filter from any electrostatics that might have been resident on the filter, and you're testing that filter purely for its mechanical function. And so that's what the A stands for. And so they have to now run an A test to be able to mark this filter as a MERV 11A. And to give you a good example, we've done a ton of tests here in our research labs, but we've seen, if you ever notice, you get a filter that comes in a plastic bag, and you open the plastic bag and take the filter out. Well, oftentimes what they're doing is they're trying to save the electrostatics. So when it does get its test, or when you put it out in the field, you get the benefit of the electrostatics for the E1 bin of particles. Well, if you run it for any length of time, you'll discharge that just naturally, and now you'll be left with just the mechanical aspect of the filter. And so you could see a MERV 11 filter that starts operating well and then degrades quickly, and it could be a MERV 8 mechanically. And so that's exactly what they're trying to avoid, is they want to make sure that if they require a MERV 11, they get a MERV 11 by mechanical means only. Notice that the UVC and now air cleaners also live in the 241 standard, but they have to meet, all of these things have to meet the testing that I pointed out earlier. So both safety and efficacy testing. Okay, and there's a cost to this. As you can imagine, everything we do in our designs and engineering with customers always has a cost that we're doing. We're thinking about, and we're helping them think about cost. If you were to just add outdoor air, now you can argue with me dollar per CFM on this one, but let's just take an average cost. You didn't increase the unit, but you can open the outdoor air, and there's an average cost of somewhere in the order of $2.50 a CFM. You'll notice that, let's take the classroom, the one that's underlined there. That classroom is 950 square feet. Based on the VRP table, it would have 33 people. The minimum ventilation requirement, if you do the calculation, comes to 444 CFM, assuming a high supply, high return for E sub Z. And you end up with 13 CFM per person. Notice that the ECA, as we said, was 40 CFM per person. So that's an additional 27 CFM at a cost of somewhere in the order of $2,190 per room. That's a lot of energy that you have to consider, right? If you scan your eyes down further, notice that transportation center. This was the number I quoted earlier. That's there. You can see that 60 CFM. But the code today, if you run the VRP under 62.1, you only need 8 CFM per person to meet minimum code standards. So that's an additional 52 CFM per person, or somewhere in the order of $26,000 of additional energy cost if you could, in fact, increase that outdoor air to deliver that much more air to that space. So as you can see, costs are important to understand. And so we have to balance that idea of the economics of what we're designing to meet the engineering requirements of what ASHRAE has laid out. Now let's get into a little bit of the code, and I'm going to show you some equations here that I think will be helpful. Start first on that top equation, and you'll notice it might look confusing, but we'll break it down. Start on the far right of that equation. You'll see the volume of ECAI. So basically, what is the total volume? You have to be greater or equal to that number, right? So you figure how many people, you multiply it by the category number. So we said, 30 people times 40 CFM, you need 1,200 CFM for that particular classroom. And you need to then figure out how you're going to get that air. The The next the next nomenclature there is natural ventilation. Oftentimes that's 0. In fact, I've never really seen anybody doing natural ventilation. So let's assume that's 0. The next one is the summation of all air cleaning systems that are basically within the room or are in the zone, right? So you could count effectively something you can wheel into that space that let's say you have like a portable HEPA unit, you plug it in, you turn it on, and it can serve, a certain square footage. You can add that as part of that square footage. You would just need to add so many to cover that entire space. Also, similarly, you can do something in the zone where you can actually cycle the air and clean that. Again, all these things count. You can also change out something within the unit. So you can have something that you might have MERV 8, and maybe you pull the MERV 8 out and you put in a MERV 11A, and now you can run the calculation and then the percentage of that air that's going to that particular space to meet that requirement. All these things count. Okay, that's the point of this equation. And so the takeaway here is, one, do we understand the trade-offs between what we're trying to do as far as cleaned air versus outdoor air? We understand those economics trade-offs. There is a cost to all these other items I just talked about. But historically, if you look at them, oftentimes you can do some aspects of simple upgrades, like upgrade the filter slightly and not add a lot of operational cost to the overall unit. And it might be cheaper to do something more locally within that space that you're trying to protect. I think it's helpful to understand the comparatives that we talked about to get equivalent adequate volume of ECA. And I think the main thing here to really recognize is that if you're doing the VRP, you're typically designing the VRP for dilutive aspects. Or the way the VRP lays out, if we walk through that equation, what you would notice is it's designed for highly dilution for contaminants of CO2 and VOCs, but it's really not designed to manage infectious particles in the air. The question is why? Well, what we recognize is particles in the air are sub 1 micron particle, and this is why you need deeper filters, more airflow, things that can move within the Brownian motion aspects of our airspace. Okay, so let's jump into the electronic air cleaners now. I'm showing you pictures of just a handful of different various air cleaners. You probably have your own in mind, but effectively, if you look under section 7.4, what you'll notice is that they make a statement here of what can apply, and effectively, as I mentioned, all apply. But this is the standard. It says this applies to all air cleaning technologies that provide microorganism inactivation. That's 1. 2, or enhanced removal from the airstream, acting alone or in combination with mechanical filters fibers. So all these things that are coming out from OEMs as solutions typically apply, and they can be anything from ultraviolet, electrostatics, photocatalytic, and ionizing air cleaning systems. And so that's actually in the standard today. Again, they must meet that effective standard, so we'll get into that standard. So the first aspect of this Appendix A is safety. Safety, has 3 levels to it. So let's go through each one. The first is what's known as the no ozone test. It's listed as the UL 2998 standard. The second is the no formaldehyde test. Effectively, what they do there is they take a large chamber, they evaporate a capful of limonene. Limonene is that lemon and lime scent that you have in all your cleaning products. So if you go to your Clorox or your Lysol or your Real Simples or those types of cleaning products, look on the back, look into the ingredients, and you'll see limonene there if it has a lemon or lime scent to it. And that is an innocuous VOC, but in the presence of a very reactive air cleaner, specifically one that's creating ozone, it will react and create formaldehyde. And so that's the test, is do you create any additional formaldehyde? Effectively, formaldehyde acts as the proxy for all air cleaning, all additional indoor air chemistry aspects. And then the last test is a particle concentration known as ISO 14644. Effectively, what you're doing there is you're setting up a clean room where they classify it. So they'll classify, let's say, the clean room as a class 6 or a class 5, and then it can't go above the order above it. So it can't go above the class 6. It can reach 6, but it can't go above it. If you set it up as a class 4, You can go to a 5, but you can't go above a class. You can't go to class 6. And I think class 5, if I recall, is the highest you're allowed to set that test up to. But to the point, they don't want you adding additional particles. Okay, so let's pause and think about this. If you were specifying a product that you know is effective, and we'll talk about effectiveness here in a minute, but you have a product that doesn't create ozone, doesn't create air chemistry, and doesn't create additional particles, do you feel confident that that's actually a really good product that you can now apply? And the answer should be yes. Those are the key aspects of what you're trying to avoid. And so this idea of setting up the test, what they require is that the test has to be set up and then run both for safety and efficacy in the same exact setup. Notice that it's done as an independent third party. Notice the size of the chamber. It has to at least be 800 cubic feet. So something like a 10 by 8 by 8 foot chamber, or excuse me, 10 by 8 by 10 foot chamber. The air cleaner has to be operated per the manufacturer's instructions, and you have to actually operate it in all fashions. So if you use that portable air cleaner as the example, you can't run it on low for safety and high for effectiveness. If there's a low, medium, high, you have to run it on all 3 settings. There is a triplicate test requirement, so you'd have to run every test in triplicate, both in the off state and in the on state. And I'll show you an example of this. And then you can't take the best case result. You have to take the average of all those tests that you're running. And then the last thing is when you're testing for effectiveness, they want you to test for using MS2. I'll speak a little bit about this later, but effectively MS2 is not harmful for humans, and so this allows manufacturers to go to a level 1 test chamber. If you were to a biosafety level 1 test chamber, if you were to do something like a pathogen that is harmful for humans, like MRSA, RSV, influenza, or even the COVID virus, all those have to be done in a biosafety level 3 test. And manufacturers do that, but they're more expensive. And so the idea and the thinking was, let's use a proxy that has similar size parameters, but can be done in simpler chambers that are less expensive and quite frankly are easier to get access to. So this is what a chamber would look like. You can see there on the left, there's kind of the door open. That's kind of the 800. That's more than an 800 square foot chamber. That's a pretty large chamber, in fact. And then notice on the right, that would be what the test might look like. So the results of the test. Notice you'll see there, right? You see 2 colors, but really if you zoom in or you lean into your screen, what you should see 6 lines, 3 blue and 3 green. And notice that they're tightly banded together. That's that triplicate test that you have to demonstrate, okay? And so then the way the ECA number comes about is you have to understand the way the test reads out. And so look at the slope, right? And that slope is important. So you would ask yourself, okay, if I get a result in 30 minutes, what's more important, the first 10 minutes or the overall 30 minutes? And likely, if you think about it, you're in a classroom or your child's in a classroom and somebody sneezes, the first 10 minutes is more important than the full 30 minutes, right? Because the more this virus is out, lingering about, the more opportunities it has to infect somebody. And so the faster you can get these out, the better. And that's really what that slope really kind of indicates. So the way the volume of air exchange is calculated there is they take the slope of the net reduction times the chamber volume. And then that gets you your VAC, and I'll show you how you get your ECA number. So key things to note here as you're from a perspective for you as the engineer is that, one, I think what you hopefully walk away with this is that the ASHRAE has done a very good job at setting the benchmark so that OEMs have to meet this minimum standard, and hopefully that minimum standard gives you the confidence that, hey, I'm designing with a product that meets the standard and thereby offers my customer and the end result very safe and very clean air that's highly effective for what we're trying to do within the 241 parameter. Notice they've closed some loopholes. So there were some aspects where people were testing in very small chambers, even shoe boxes. They were, you think about it, you can take a portable air cleaner, and there were examples where they were sticking in a box that was just bigger than the portable air cleaner, and then they were giving you what they called their CADR rating based on that, their equivalent clean air rating, or sorry, their clean air delivery rate rating. But it wasn't really done in a very large chamber. It was done in a chamber that air could manage the airflow for it, and it didn't extrapolate out. Notice that you have to configure the test, and you have to do that test in multiple different ways, and then the net reduction for that test has meaning to you. Okay, so this should give you a lot of confidence for when you're applying something, how to apply it, and then how to extrapolate it into a real-world scenario. Obviously, these tests are being done in a lab, but notice within the testing report some key things I want you to remember and look for. First thing is, did the third-party test report detail out how they did the test? Did they show the results? Did they demonstrate repeatability? Did they describe the chamber size? Did they describe the surfaces, where everything was? Typically, they'll give you a graph to show you where the equipment is laid out. They also have to demonstrate the measurement of the equipment, the accuracy of that equipment that they calibrated. There is a noise listing too. There's no pass or fail, but just so that you recognize, you could potentially be adding something that is creating too much noise. Great example is that portable air cleaner. Oftentimes what you might hear is people had a portable air cleaner, but it was too loud. The teacher couldn't talk over it, so they were turning it down. You want to be careful of that. And then if you're going to use a UV product, did they measure the electromagnetic radiation level of that UV? And did they compare it to the safety thresholds that were in the safety limit? Okay, those are some of the key things you want to look for. Again, you're going to get this presentation. I lay this out here so that you have it and you understand it, and effectively can ask any questions here while we're going through it. There's also this nice chart that we put together. Again, was the testing done in triplicate, not duplicate? Did they use the average and not pick the best? So on. Notice some other things here. The temperature of the chamber has to be stable. You can't have wide variations. The triplicate results can't have wide band either. So even though they do it in triplicate, were the test results within a plus or minus 5% of each run? If they were very variant, there's something wrong, and you want to kind of dig deeper on that. Did they test it in all modes? And obviously, did they give you the slope reduction? So there again, you see a slope reduction. Notice how they've calculated. They take the KT sub D, basically the air cleaner turned off, then they compare it against the air cleaner turned on, and then they multiply that by the chamber size, and that gives you your volume of air, and then they divide that by the amount of air to get you your ECA number. So in this particular example, the ECA there would be, rounding up 213. Okay, so that then you could say, okay, this air cleaner provides 213 CFM of equivalent cleaned air. Let's say you have 10 people for easy math. That gives you an additional 21.3 CFM per person that you can add. Okay, so the report also has this quick little green, red, like green pass, red fail. And the things you want to look for, right, are the key three safety things we walk through. Formaldehyde, did it pass? There's a lot of the detail on the test methodology. Effectively, they have to be less than 50 micrograms per cubic hour. Ozone, did it pass? The testing equipment has a band of 5 parts per billion, so you have to be less than that 5 parts per billion, but that's the accuracy of the equipment that's being used. And then the particle test that we talked about in IsoChamber, did it exceed? And you could see all that, and then you could see also the noise requirement listed there as well, or the noise results listed there as well. Okay, so you're looking for a pass, and an OEM should be able to hand you their 241 testing for that equipment if they claim it complies with 241. I don't want to go through the perspective here. I think I just hit them all, but effectively, I think what you could see here is this is a very well done setup for you as an engineer, not only to get confidence, but then also to do evaluations of all this equipment. That's what ASHRAE was looking to do. That's why I mentioned at the beginning, if you read that introduction, what they hope you gain out of this is the confidence that if something meets 241 and you're designing to provide better protection within that space, whether it be a classroom, a school, a senior living, daycare, hospital, healthcare settings, dental clinics, what have you, you've done your homework. The OEM that meets that requirement, and you get a really good result at the end. Okay, so filters, as I mentioned, can also comply. So you can pass air through a filter and get an ECA score, but effectively it has to be a MERV A rated filter so that you can get the proper rating. So not only MERV 11A, but it could be MERV 13A, 14A, 15A, alike. All of those things require an additional test that the OEM has to do in order to meet that. It does not require a safety test, as you can imagine, but here is the weighting. And so you'll notice if you took a unit that you had a MERV 8 and you put in a MERV 11A rated filter, you can now take a score of 60% of that air that goes through that filter as part of your ECA score. So if you're passing 1,000 CFM through that unit with a MERV 11A, you can count 600 CFM leaving that unit as equivalent clean air that now gets distributed throughout the space that you can count. Okay, that's how that works. Pretty simple. Obviously, a HEPA filter gives you 99%, and then you can see the scores range between 60% and 99 between those MERV ratings and the HEPA rating. Okay, so now let's get into the actual calculation. So as I mentioned, you can download this off of ASHRAE. They gave you a calculator. I'll blow this up in a minute, but just at high level, what you do here is you kind of select what is your base case, so you can see where you're starting, and then you add different options as you go through it to see what contributions you're adding to the ECA. And then at the end of the day, you can kind of compare your economic value versus the ability to meet ECA. That's effectively how this tool should be used. So our first example is going to be a classroom. Okay, it's 950 square feet. I'm taking it right off the VRP. You'll notice we're going to supply 1,500 CFM of air. We're going to meet that VRP, the 62.1 VRP, the exact same scenario I walked through earlier. So so many CFM per person plus the square footage, CFM per square foot divided by an E sub Z of 0.8 for high supply, high return. And that gets you to a 444 CFM of outdoor air. Your occupancy zone will be 33 people. You'll notice you have a MERV 8 filter, no other additions there. And if you now look down the assessment where it says existing, what you'll see is the ECA score for that comes out to 13.4. That's good, but doesn't meet what the 241 standard requires now, which is 40. Okay, so we got to get from 13.4 to 40. Okay, so test one would be, let's just replace the MERV 8 filter with a MERV 11A filter. And that gets you from 13.4 up to 32.4. Great, but still short. Okay, let's try a MERV 13. Notice you get a little bit more value. You get 37.8. But again, there's a cost to that filter. That filter is very expensive. There's also an operating cost. You're pulling more air, or you're increasing the pressure through that filter, thereby putting more stress on that fan. Okay, so what if we went back to a MERV 11, and now you added an air cleaner that has an ECA score, in this case of 275. In that case, now you meet it. Okay, and now you can evaluate, does that air cleaner at 275, what is the cost of that? So that's how this thing works, is you add all these things together, and it's very layered in its way in which it's going to help provide protection within the space to meet these requirements. I'm going to do one more here just as a good example. So this is a waiting room. Okay, so a healthcare waiting room, 400 square feet. If you actually read the code under the VRP, you're allowed 60 people in that 400 square feet. So we're going to say, okay, let's take the 60 and let's lower that P sub Z, as I mentioned earlier, and let's have 30 people wait in the car. So now you're going to design this around 30 people. Okay, you have a MERV 13 filter as its base case, and that gets you a E sub Z equivalent cleaner of 52.7 in the way this lays out. Okay, so first test is, let's just try a HEPA filter. So a HEPA filter gets you to 66.1. You go from 60% up to 99%. You do get some value there, but again, that's a very expensive option typically if you're replacing a lot of HEPAs. And it's also a high pressure drop. Okay, so let's go back to the MERV 13, but now let's just add some air cleaners in that space that meet the standard. And those air cleaners, what did we add there? 1,200 equivalent clean air of air cleaners. So each one being let's say it was 300 ECA, so you added 4 air cleaners, maybe 1 in each corner, or something in the space that had a lot more value to it, and now you meet your 90 CFM per person, you're at 92.7. Okay, pretty simple in the way that lays out. Last thing here to kind of understand is that, MS2 can be considered, even though it's a surrogate, it's a poor surrogate for a few reasons. So one, you're not really getting a good result of what happens with real viruses. It's one of the complaints that was going back and forth, and ASHRAE needs to address this. But if you have known aerosolized pathogens in the air, things that are commonly having a year problem, so things like influenza, MRSA, RSV, those are real viruses that we're trying to avoid against, we're trying to protect against and design for. That should be something that could be added into this and provide better control. And in fact, OEMs will give you their equivalent ECA for those, but it doesn't comply with the MS2, in part because MS2 is actually an open envelope virus and actually doesn't react the same way as those viruses do when you test them for an electronic air cleaner. And so that actually is you're getting less credit than you should when you add some very good electronic air cleaners to your space. Use their science, and you can add this to it, but just recognize that there is a disconnect there with MS2. The other aspect of MS2 is, if you notice, the filter testing that they require is 52.2. They're giving you a lot of credit for filters, and the 52.2 test doesn't use MS2. It uses Arizona road dust effectively. It's a wide dispersion of particles, and MS2 is a much smaller product, and so you actually don't get the same pass-through benefit that you get with Arizona road dust. You get more there than you would with MS2. And so you're getting more credit for filters, less credit for electronic air cleaners. So that's an area that they do need to kind of address as they go through this. But nonetheless, recognize this is a good baseline for safety. It is a good baseline to kind of get started. And ASHRAE has committed to continual maintenance on this. And I hope that they'll address this aspect of those two pieces there in an effort to try to continue to provide direction and really ways in which you can give you confidence that these other products that are coming into the market do provide safety for the air. And that's really the conclusion. I hope I really demystified 241. I know I got into a lot of detail there, but I trust that you guys took a lot away from this. I know it's in some cases it's eye-opening as you guys are thinking about how to apply 241. I know in your market, I've actually talked to a handful of engineers who were designing already for 241 based on request, and in some cases, the provincial government is looking at it. And so we're happy to help you. I'm here with Odell. Odell can help you with a lot of these things, and then I'm also willing to help as well. But from the perspective of just this PDH and this presentation, what I want you to walk away with is this is a really good thing to add today, even if you're not looking to meet 241, just from the perspective of safety, that you get products that are safe and meet your design and requirement. Last thing, and I think I'm allowed to say this, I'm allowed to give one plug. I'm wearing my Smart IQ shirt today. Odell represents us with Smart IQ. Our product was designed for a handful of standards, one of which was 241. If you're interested in learning more about how our product meets 241 and how it can help you in your designs, we would love to talk to you. You can reach out to me or you can reach out to Odell. With that, Caleb, I'll turn it back over to you for any questions, and then we can go from there.
Appreciate it, Tim. That was a very good presentation and very informative. If you guys have any questions, please share in the chat, and I will share with Tim. And I just want to let everyone know that by tomorrow, you guys should receive a certificate for CPD hours for the PEng as well.
Did anything come through on the chat feature?
Nope. No questions so far. If you guys have any, please share.
I saw a clapping hand and a thank you from Mala, so thank you guys.
Thank you.
Thank you. Appreciate it, Phil. I will be in town for those who are still on. I will be in town, coming into town in a couple of weeks. Yep. Was that what it was? First week of April I'm coming in?
Yep.
Yes. So I will be in town the first week in April, that 31st week. For any of you who are interested, engineers, contractors, and customers on, please reach out to Galeb, and we would love to kind of continue the conversation that way as well.
I do have a question here. What's from TJ? What's the effect of adding more filters and cleaning air on humidity?
Oh, so ostensibly, I would say you don't see a lot of issues, but it would depend on the product. So if you're adding filters, I would say nothing. If you're adding a product that's adding something into the air, then you got to think about what it is, in fact, adding into the air. That's partly that particle test, but it doesn't look at any humidity. If you add more heat into the air, and I think that's probably where you're going with this. So some products are actually doing their doing their infection control by adding something that's heating that air up, depending on how much call it sensible, basically, load they're adding. You can, in fact, maybe change the latent load on that, and that might be critical depending on what you're designing. If you're designing something for industrial use, like my background was in designing for pharmaceutical clean labs, that would have been critical. If you're designing something for an office or a waiting area, I don't think you're going to have too many problems. You're meeting that wide bandwidth of humidity control. Abraham, yes, I will send a copy to Galeb of this presentation in a PDF form for you. And you guys, and I guess if anybody who wants it, just send Galeb a note and he can pass you the presentation.
Yep, I can do that. Any other questions?
Okay. Well, I look forward to meeting many of you as I come through come in your office. Hopefully, we have some of you scheduled. For those who do have additional questions or are more interested also in our product, reach out to Odell and we'll set up a conversation. We can do it virtually like this, or we can do it in person. Thank you, everybody. Appreciate your time today.
Thanks.
Galeb, I'm going to hit the end event. I think that's what I'm supposed to hit here.
Okay.
Okay. Thank you.
One question came in from Sohail, but we can send him an email.
Go ahead. Yeah. You want me to answer it this way, or you want me to answer it by email?
Not sure if he's still there or not, but we can maybe for the rest of the people that's still here. Is there anything in the new standards about proper clean air placement to reduce turbulence, prevent mixing clean and dirty air, like displacement ventilation versus turbulent standard diffusers?
Yeah. So no is the answer. There's nothing in the standard. The standard focuses, as you saw, on safety of the products that you want to add and how might you calculate additional cleaned air. But it doesn't necessarily address turbulence, displacement, air, anything to that effect. That's assumed, or I would say that's silent in this particular standard. But it's not a bad thought, right? So how you're mixing that air, you do want to make sure that you're cleaning the air that you're trying to clean and not clean the air that gets ejected out or is mixing in the wrong way. So yeah, good question. I can answer it directly with him if he's curious.
Yeah, awesome. I will, we can reach out to him and we'll send him the answer. No problem.
All right. Yep. Thank you, everybody. Appreciate your time.